the power.
Excellent.
And now I will say, there's only make host. There's no make co-host, but let me
Yeah,
see
they
if
used
I
to have that.
Okay, make host. Yes, change host. Okay, now I'm recording. Cool. Okay, so I think we can begin. So I'm happy to have Sarah Chasins here talking to us online in this seminar series that we're having. And so Sarah will be joining UC Berkeley as a professor. She was there as a PhD student, and they just couldn't let her go. She's been working at the intersection of PL and HCI, so she attends both, PL conferences as well as WIST and Dub and conferences like that. And she's been working on program synthesis, I would say, or automated programming with a particular emphasis on social scientists and domain experts who may not necessarily be trained as programmers. So Sarah, go ahead.
Awesome. All right, everyone get ready to participate. This is my first time trying to do interactivity in Zoom, so we'll see how it goes. So I'm going to be talking about how you can get a non-programmer to write a program in 5 minutes that your average CS PhD student can't write in an hour. Web automation programming, it's a lot about manipulating web pages programmatically, often to collect data or to enter data. And so naturally, it's usually limited to programmers. This talk is about how I put web automation programming in reach for people who would consider themselves non-programmers. And I'm also going to use this domain as an opportunity to talk about the broader area of usable programming. This idea that we can bring together techniques from programming languages and human-computer interaction to democratize programming. Throughout the PhD, as mentioned, I had some really close and long-running collaborations with social scientists, and so that's shaped a lot of my work. And I'm going to talk about some of the really interesting and exciting research challenges that sort of fall into your lap if you work on the programming needs of non-traditional audiences like them. So with that, let's dig in on web automation and how I use techniques from PL and HCI and developing novel reformulations of traditional program synthesis problems in order to really make programming techniques that work for real non-traditional programmers. So here's the part where you have to click on the participants icon and get ready to press yes or no. So who here has already written a scraper? If you have ever written a scraper, press the yes button. If you have never written a scraper, press the no button.
You mean raise hand or?
I think it should have the green and red yes and no, although I actually don't see it on here.
If I click on participants, I have raise hand, and that's it.
All right, well, let's go for raise hands then.
All right, well, let's raise hands.
Okay, so definitely some folks here do have some expertise with web scraping and have realized the value of web data. I think that's really exciting, and I'm really excited to see that more and more people are realizing the value of web data. But what I'm actually most interested in is how the composition of those folks is changing over time. So right now, most of the people who are getting access to data and realize the value of web data are the folks who already know how to write programs, so the people who have the kinds of skills that we in this Zoom room have. But going forward, more and more non-coders are realizing the potential value there. The problem is that it's hard for them to get a hold of it. But I'll give you an example of why non-coders might actually want this data. So these are some sample tasks from my current social science collaborators using data sets that they're collecting with my tools. So in sociology, folks are trying to help low-income families move to high-opportunity neighborhoods, basically by collecting a bunch of rental listing data. And they're going to use that working with housing authorities to set the threshold prices for housing vouchers. In nursing, folks are looking at, okay, how do we reduce the effects of perceived race, perceived sexual orientation on medical crowdfunding outcomes by looking at sites like GoFundMe. So there's all these interesting questions that they can ask, but somewhere along the line, as you start developing a tool like this, you might ask yourself, is end user web automation actually a real need? That's certainly something I started to wonder as I had sort of an early prototype of Helena, which is my web automation language and tool. And so I sent a little email out to a listserv that had a bunch of social scientists from various fields on it. And I said, do you need web data? And I was expecting to get a few responses, maybe get a feel for the kinds of data that they might need. And instead what I got was just a flood of emails that lasted for the next 24 hours and made it really hard to get anything else done for that time. It turns out that yes, people definitely want data that is out there. They know about the data that they want. Unfortunately, they just can't get it on their own. With the tools that they have access to right now, it's just not enough to actually get them this data. And the reason is that web automation programming is really hard. And so this is computer science PhD students, and you can see that even after an hour, we cut them off after an hour, only about a quarter of them actually managed to complete this web automation task that we set them. But if we give them the right tools, we can get to 100% completion rates. You can see here with my tool, within 10 minutes, everyone has actually completed the test. So it is doable. So let's do a quick quiz to explain why web scraping is so hard. So get ready to unmute yourself and shout out answers. So say your goal here is to scrape the product price over time. You can see here's our little product price. And what this is doing is going through the nodes and saying, give me back the node that has $26.06 in it. Now, I'll tell you right off the bat, this little snippet is not going to work for our goal. Does anyone want to shout out why it's not going to work?
The value may change.
Exactly, yeah. So as soon as the price is no longer $26.06, all of a sudden that's not going to actually get us the information anymore. And so what we need to do if we actually want to get this price over time is basically reverse engineer the structure of the web page. Let's try another one, a little harder. So the goal here is we want to scrape the first entry in the Google autocomplete. And what our first line there is doing is it's popping our query string, in this instance in the image there, it's web scraping. We're popping that into the value of the search box. And then we're going to the place where the first autocomplete entry will appear and grabbing that information. So why is that not going to work? I told you web scraping is hard.
They might change the name of that field, or.
That's true. That's a good point. That's not even the one that I was going to highlight here, but that is a really good point. So the key problem here is that actually that autocomplete is never going to show up. So underneath the surface, when you are typing into that autocomplete, or when you're typing into the search bar, what's happening is all these low-level DOM events are happening, and then the web page can respond to those with various JavaScript handlers. And those JavaScript handlers getting triggered is what actually causes the autocomplete menu to be displayed. And so if we don't trigger that JavaScript, the autocomplete menu never even shows up. And so there's nothing to grab for when we actually go and look for that autocomplete item. And so what about here, where the goal is we want to click on a product variant, maybe we want to click on, variant number 2 here, and then we want to add it to our cart. And so what's happening is we click on this button and we click on this button. Why is this one not going to work? This one's a hard one.
Might not be logged in, session expiring. No.
Oh, sorry, I couldn't hear that one.
You might not be logged in, or the session expires, or I don't know.
That's true. But there's actually
and different variants have different URLs, no?
Yeah, and so this is what really is the key issue most of the time. So definitely getting logged out could be a big issue. But in this case, what's usually the problem is that you're going back to the server to grab that information about the second product, right? So that hasn't been loaded into the page yet. And so when you click on that as a human user, it all gets grayed out, and you take that as a visual cue that, oh, it's not ready, right? It's communicating with the server, something's happening, we shouldn't proceed yet. But there's nothing that actually stops you from clicking on that add to cart button. And when you click on that add to cart button, what happens is the old product variant, the one that we were trying to click away from, actually is the one that gets added. And so in order to actually do this web scraping task, you have to also reverse engineer how it's communicating with the server, all the AJAX that's happening underneath the surface. So there's all these tough tasks that just make it a really hard thing to do. Now, if you're looking at this from a high level, one thing you might say to yourself is, well, all that's really happening is the user is taking some actions, the browser is getting those actions, using that to get some data, showing it back to the user. Let's just watch what actions the user takes, pop that into basically an imitation user, some kind of robot that's going to do this for us, and have them take the place of the user and interact with the browser. So this is basically the key idea behind programming by demonstration. And here's where you can tell that this talk was not originally intended for a PL audience, because we're going to quickly explain program synthesis. So of course, with program synthesis, the idea is you give some synthesizer a spec, and the synthesizer is going to write the program that actually fulfills the spec. You might be familiar with programming by example, where the idea is you get input-output pairs. That's your spec. You give that to the synthesizer gives you your program. What we're talking about today is actually programming by demonstration, where you don't just get the input-output pairs, you also get the sequence of transformations that the user did in order to get to the output. So this is a problem that people have been trying to tackle specifically for web automation for a long time, ever since it made sense to talk about Netscape Navigator and recent versions of Windows 95. And sort of the first thing that people started thinking was, well, it looks like there's a logical table on this web page. Maybe I want to extract that table. And the next thing was people realized, well, people are interacting with pages. Maybe we want to sort of record a trace of the interactions and then replay it. That could be useful for testing. And then around 2009, we still hadn't reached the point where we had this sort of complicated web extraction programs that, say, my social science collaborators need. And then the web started getting even more complicated. It got even more interactive. people are starting to do this SPA approach where everything is one web page, and then it's sort of going back with Ajax, and it all got really complex. And at this point, we basically stalled. So I'm going to talk about sort of the demonstration of the tool that unstalled us. And to do that, we're going to do a quick little live demo. We'll see if that works over Zoom. So does anyone want to unmute themselves and say what data they would look at, what website they would look at to figure out when CS researchers peak? Any ideas for web sources for that info?
Scholar.
Yeah, so Google Scholar, we'll do that. All right. So here what's going to happen, I'm going to move this. Okay. So can you see sort of a Google Scholar webpage here on my screen? Hopefully.
Yes.
Awesome. All right. So we're going to start up my little Chrome extension, and we're going to demonstrate how we would collect information about the first row of the data set that we want. So information about the first author and the first paper by the first author. You can see over here, we can see that first row that we've collected. Now we can go ahead and stop recording. And what's going to happen is it's actually going to, so first it's given us a representation of here are the actions that you took. And then the next thing that it's going to do is it's saying, okay, you interacted with that first author, maybe you want to interact with all the authors. And then the exact same thing for papers. You can see it had a nice name for papers, but it didn't have for authors. But that's okay, it's still going to be able to find the information. And so all that's happening is we're loading up that URL. We're going to do some stuff for each author, including clicking on the author's profile page, and then we're going to go through the list of papers, and eventually we're going to add a dataset row that includes all the information. So that's the program, and we can go ahead and run it. And what we're going to see is on the right, we're going to see the web page that the tool is actually controlling in order to get access to the information. And then once we've actually extracted some data, on the left, we're going to see sort of the preview view of that data set that it is actually collecting. And so over here, we're going to be counting the number of rows that we've collected so far. You see so far we've got 20, we've got 100, and that's just going to keep going for about 3 million rows. So we're going to go ahead and pause that and come back to our keynote here. So I hope that after seeing that demo, you're thinking to yourself that end user program synthesis seems pretty easy and people should like it. That's certainly what I expected. But it doesn't seem like we're actually seeing adoption of these tools. I mean, anyone please feel free to shout out if you regularly. Oh, was there a question?
A question? Yeah, I was a little confused by actually what you were trying to grab. I thought you were trying to grab for each researcher their top paper. But
yes.
What you just had a whole list of things for Jeffrey Hinton.
Yeah,
it
so actually,
looked like it went down and scraped a lot of stuff off of Hinton's page, which suppose that were not my intention, and I just wanted the top paper for each of those. What would I do differently?
Yeah, so we could limit it and say just collect the top paper for each author. So if I had let that keep going, we would have seen that it was going to go on to the next author and the next author. Because the way that we actually end up analyzing this data set is by looking at when they publish their first paper versus when they publish their most cited, we actually do want all the papers by all the authors for this particular data set. But yes, you could absolutely go in and say, no, only give me the first. I don't need to actually generalize over all the papers.
Another question.
Yeah.
So Scholar, as far as I know, has some kind of an anti-scraping technology. Yeah. So you would stop at what, 20? Because sometimes I do a literature survey and it says you seem to be scraping. I'm not going to give you more pages. So what do you do with that?
So there's a couple of different ways that you can handle that, and there's a couple different ways that our tool handles that. So one is if you're too fast in scraping, you end up having to add some delays so that you're not overloading the server. So you can directly go around, and I didn't actually show you how we would edit these programs, but we could go over here and we could say, let's actually add a wait, 1 second thing. And that would be a way to get around it, but it would be very slow. One thing that we do is because the programs that we're actually creating are very user-like, they're basically triggering all the same low-level DOM events, which we're going to be talking about later in the talk. It ends up not triggering any of sort of the normal bot detection things. And what does trigger in the end is that timing. And so the way you can get around it is you can do this wait 1 second situation, or what's much better, of course, is to distribute it. And I'm going to talk later about how we can parallelize and distribute these scripts.
Great,
so
thanks.
there are ways to get around it.
I have 2 questions.
Yeah.
The first one is that in Google Scholar, for example, I think there's a more button at the bottom of the page, and then you have to click it to get the rest. I don't know. Is everything loaded already, and you just
no? So if we had watched, we could actually I'll go ahead and have it keep going. you'll see that it's actually scrolling down and clicking on that button. So the things that it highlights in green are the things that it's actually interacting with. Oh, and I didn't scroll it all the way down to the bottom. But you can see that show more button. Eventually, it's going to actually click on that.
Oh, how does it know? Because you did not demonstrate that.
That's right. So this is actually a table that has already seen in the past. And so it knows already how to interact with that more button.
I see.
I'll actually close this one, and then we can actually take a look at what it knows about this papers table. So edit this table. The page shows my table. So you can see that it knows that it uses a more button on this one, and it will actually show you that's the more button.
I see. That's cool. And the second question is, I mean, you have this, I forgot the name of this language,
Helena.
the teaching, no, the shape, the graphical language that you use.
Yeah,
semi-graphical, I guess. So are you're expecting users to know how to edit this, or is this just your view? Or
yeah, so if they want to do something other than sort of the defaults, if they want to go in and say, actually, I need to wait 1 second between, you know, each of the papers in order to, you know, slow it down enough, that sort of edit, they need to be able to do exactly what I showed, where they can, you know, go in here and pull in their blocks and do whatever it is they want to do.
Cool.
But if they just want to run sort of the default, which is what I showed in the original demo before we started playing around with it, they can run that without having to understand anything about what's happening here. Yeah, good question. All set for now on questions? All right, we'll head back to the keynote for now, and we can come back and play with the tool more if we want to. Okay, and so it turns out that people haven't really adopted end user program synthesis tools, which is a little surprising, at least to me. But basically what this means is that over the years, we've learned a lot about what users don't like in end user synthesis tools. And then this talk is going to be about what they do, what will make it so that it's actually useful to real people. So let's diagnose what's going wrong. So there was a beautiful paper by Tessa Lau that basically looked at what are some of the problems with programming by example and programming by demonstration tools. And one of the things she realized was that if the user is given 5 repetitive demonstrations, and then they have this tweak in mind that is really straightforward to them, something they can imagine saying in natural language, and it seems really just simple, it's really frustrating to have to go in and give your 6th repetitive demonstration. We also looked at the web automation literature and realized pretty quickly that it's very frustrating for users to have to do multiple different kinds of demonstrations, which is something that a lot of them ask for. And then there's the Excel flash fill story. So this is sort of the success story of program synthesis tools for end users. And one of the things they did to actually get it into Excel was study what users want. And it turns out if after giving one example, they get the program they want, then they are happy. And if they do not get the program they want, they are not so happy. And so the question that this led me to is, could we do programming by demonstration with just one demo? That's sort of the common theme throughout all of this. Let's get one demo, one example. But of course, if you're a program synthesis person, you say, no, that's wild. This is just a very ambiguous specification. That's not enough information to go on. And of course, it's true that it's very ambiguous, right? If we just give this demonstration of how to collect information about one paper by one author, well, do we want the first paper by each author? So this is sort of relates to the question that we asked earlier. Do we just want the first paper by each author? Do we want all of the papers by all of the authors? Do we just want the papers that have more than 20,000 citations? Do we just want the papers that mention the word learning? All of these are consistent with the demonstration that the user actually gave. And so the observation that guided my approach was that drafting programs is really hard for these users. They have this blank page syndrome. Looking at that blank editor windows is really, really intimidating. So a lot of them have been trained in programming in a very small domain, right? They can do data analysis programming in particular, and they've had 1 or 2 semesters of Python or R specifically for that task. And even in that domain where they've already been trained, they actually don't start with a blank editor window. They take a script that they've already used in the past, and then they tweak it until it works for their current project. So drafting programs is hard, but editing them is easy. That's something that they feel comfortable doing. And this led to basically my reformulation of the program synthesis problem for this domain. So with traditional PBD, what you're gonna do is you're gonna pile in a bunch of demonstrations. The synthesis algorithm pops out a program. We run it, we ask the user to inspect the output. If the output is what we want, we say, great, we're done. If we don't like the output, we go back in, we give another demonstration, we start the cycle over. But that has the multiple demonstrations problem that we don't like. So the key idea behind the technique I talk about today is demonstrate once, revise anytime. And so this gets back to another of the questions that we talked about. Do we expect the user to actually interact with that program that we showed? And And so the answer is, if they want to tweak it away from the default program that we synthesized, then yes. So basically what's happening is they'll give one demonstration. The synthesis algorithm will use that to come up with a draft program. But it's a program expressed in a learnable language so that the user can directly edit it and tweak it until it meets their exact needs. So this is the demonstrate once, revise anytime, or DORA approach. I want to take a quick moment to talk about why one demonstration really is better than, just so much better than multiple demonstrations. So first, we already talked about the fact that it leads to happy and successful users. It also changes our task as the synthesizer implementer to make it much easier, because all of a sudden we don't have to be able to reach every single program in the space. It's okay if we can make it to a program that's close to what the user needs, just close enough that they're able to tweak it into what they actually really want. And it also changes it so we don't have to provide a lot of sort of supporting infrastructure that isn't as fun, or might not be as fun for some implementers. But the other big thing is that it actually changes the class of programs that we can attack. So all of a sudden, programs that take days and days to run, you're not gonna be able to do that with this traditional PBD approach where you're gonna look at the output to figure out if it's okay. Here, it's totally fine if the output, takes days or hours to come up with, as it will for some of these scraping problems, because we can actually look at the program in order to debug it. You don't have to just look at the output in order to debug. So it changes what programs we can tackle. Is there a question? No, we're good? All right. Okay, so basically what this DORA workflow is going to break down into is usable drafting tools and learnable languages. And of course, both of these are useful also outside of DORA workflows, but we're just happening to talk about it in this particular framework. So I'm not going to be able to dive into all of the sort of research questions that drove the Helena work, but I'll dive into 4. So the first goal, synthesize a complex program from a single demonstration. How do we then make these programs robust to the fact that the web pages are always changing? We also want to make them both robust and human readable at the same time. And finally, we actually want people to be able to parallelize so they can tackle the really big tasks. So basically, the common thread across all of these is that the approach is to throw out the standard synthesis or compilation problem, because either it's hard for the user to produce the spec, or it's hard for the machine to turn that spec into the goal, into the program that we actually want. And let's make a brand new formulation of the synthesis or compilation problem that both makes it easy for the user to write and makes it easy for the synthesizer or compiler to actually produce the thing, or at least doable with help from some smart synthesis design work. And as you can imagine, this breaks down into basically HCI and PL components. And it's really important because we are trying to design whole new problems that really make it easy both for human and machine. That makes it so that we really have to have HCI and PL expertise at the same table. I have a couple ideas about how we should sort of do this bridging, how we should do usable programming, and questions that should guide people. So the first thing I'd like to suggest for folks to do is figure out what's hard or easy for users. What do they find hard or easy to express about their problem that they're trying to tackle? What do they find hard or easy about traditional programming? And of course, we also have to go in knowing what is hard or easy for synthesizers, compilers, the various tools that we could be building for them. And then the third and most controversial part here is that we're in this really strange domain when we are building programming tools for non-programmers, because most of us doing this work are programmers. And so we and all of our programmer friends, when we see a particular problem, we want to solve it in a particular way, the way that we've all been taught. And it's really tempting to try to push on that solution, to ask end users to solve it in that same way, and really push on that one fancy new solution that will tackle the exact same problem. But oftentimes that's not actually the right approach for these audience. We actually need to find a new problem formulation that is going to have a simpler solution that is going to be in reach for them. And so that's going to be the guiding thread through here. So let's talk about first what users need. And so this started with a formative study to figure out, okay, what are people actually trying to get access to? So first, multi-load data. They are not just going to one web page and extracting all the data they want from that one web page. They are doing clicks, they are interacting with forms, they're typing, they're interacting with widgets, all the same things that we do to browse the web, they're doing to collect data. And then the other really key point is that they actually want hierarchical data, so tree-structured output data. They don't just want a list of authors, they want a table of authors and a table of papers, and they want to maintain the connections between those, right? So this all gets organized into sort of the tree-structured hierarchical data that you would expect. But why is this so hard? Well, it's because in order to collect this hierarchical data, we're going to need nested loops. And so now if you're a program synthesis person, you're getting very nervous. So the set of allowable programs with no loops, it's big, but maybe it's manageable to search it. What if we add one loop? Well, now it's much bigger and it's going to get a lot harder. If we're allowing multiple loops, if we're allowing multiple and nested loops, this is a massive space. How are we going to make a synthesizer that's actually going to scale to this space? And so this is where we hit sort of a fork in the road. Often what we do when we reach this point is we say, all right, let's build a stronger, faster, better synthesizer. But we've pushed in that direction and it hasn't delivered the class of programs that these users actually need. So is there some other way? Is there something else we could do to deliver these programs? So let's take a moment to think about the possible demonstrations that we could give. On the left, here's a demonstration where we're sort of playing around with a couple of the papers that we want to get, and then we go back to the author list, and then we're messing around with some of the authors. That's one demonstration. There's also a demonstration that I actually gave in the demo that I showed you in the live demo, where we are interacting with one author and then we're interacting with the first paper by the first author. Both of these are reasonable demonstrations for a human user, but one of them is a lot easier for the synthesizer. So if we allowed both of these, we can't really do anything smarter than just searching the space of Helena programs until we reach something that produces the output that the individual demonstration has produced. If we, however, could just limit the user a little bit, we could do something a lot smarter. And so what this really comes down to is the fact that there's a class of the possible demonstrations that the user could give that is friendly for the synthesizer, something that we know how to write the synthesizer or the compiler that takes those particular subclasses of inputs and turns them into the output programs we want. And for anything outside of that, we just don't know how to write that synthesizer or compiler. But if we push this too far, we can get away from the user friendliness, right? So we talked about those tools that were very synthesizer friendly, but they demanded too many demonstrations and it was bad for the user. And so of course, what we really want is to find something at the intersection. And the particular way that I have enforced that we do something at this intersection is by having a contract with the user. And of course, this isn't actually how I would express it to an end user, but basically the contract is we're gonna ask them to demonstrate the first iteration of each loop, so collect the data, the first data row in each table that they want, ordered from outer to inner loop. We are helped in this by the fact that the web basically enforces that you're gonna traverse it in that way. And so this contract reduces the synthesis problem to a much smaller problem, still a complicated problem, but much simpler. And basically, all of a sudden, all we have to do is figure out where in this straight line program do we want to insert loops and over what tables. So where do the loops go? Let's start by assuming that we actually know what tables are interesting to the user. Big assumption, but let's say we know about it. Then we can label each of the actions that the user took with whether they interacted with a cell in the table. And then all we have to do is go ahead and actually add one loop for each table, starting before the first use of the table's cells and ending after the last use. Pretty straightforward. Now it's true that it was sort of a big assumption that we actually know about what the tables are. So here we're going to do some of our hand raising and or yes knowing again. So it sounds like people want to do hand raising. So let's do that. How many people think that all of these nodes that are highlighted in red are part of a logical table? So there are other rows that have the same structure elsewhere on the web page. Raise your hand if yes. Yeah, so I agree. It looks to me as though there are going to be other rows that have the same structure. There are going to be other papers. All right, so let's take our hands down for that and we'll go on to the next example. So here on Craigslist, we have a bunch of information about a particular listing. Do we think there are other listings also on this web page, other things that have that same structure? Yeah, I agree. Oh, maybe I don't agree. So to me, it looks like on the same web page, there aren't going to be all that many, there's going to be one listing on this web page. And so we're not going to see other information on the same web page that also takes the same structure of, posted 12 minutes ago and this particular price. This is all about sort of one. And then what about here? How many people think that on this page, we're going to see something else that has all of the same structure elsewhere on the page? Yeah, this one's confusing, right? Because obviously these ones on the left, it doesn't look like there's anything else structured like that. But for these ones right here, yeah, absolutely. There's other tweets on this page. And so we're going to basically take advantage of that same insight that you used when you were looking at these pages. This is the table selector synthesis problem. We start with the record time web page and we see some interacted nodes based on just what the user interacted with. And then we want to go and turn that into a table selector. So it has to have more than one row. We don't just want that trivial table that has just the one row that the user interacted with. But we want to make sure that as many of the nodes that were interacted are part of that first row as possible. And so basically what's going to happen is, let's start by guessing that all of the interacted nodes are in the first row, and we'll back off to subsets. So let's start by guessing that all n of these are in that first row. When we look around for other things that have that same structure, well, we don't find it. So let's try subsets of size n-1. We try again. We still have this one highlighted. So, we're not going to find anything else that has the same structure. But eventually we get to this one that has n-2, and it has only these ones. And now we find that this has the exact same structure. And we're going to say, okay, it looks like we've found the table of interest. And so basically, we're just taking advantage of the fact that there are some web best practices that say data that is logically similar is also going to be structured similarly on the web page, basically generated from templates. And so this turns the problem from searching the space of all the programs in the Helena language to this much simpler, still complicated, but much more constrained table selector synthesis problem. And from the perspective of the user, they go from having to reverse engineer all of these complex web internals to just having to learn this demonstration contract, much more manageable. And the end result is that users do perceive Helena as more usable than sort of traditional web automation programming. Also much, much more learnable. It's an even bigger jump there. And also they're actually more successful. And so of course, this is coders, right? This isn't non-coders. We're not gonna expect them to learn Python and Selenium within the space of an hour. But you can see that we can go from having a 25%, 27% or so success rate to 100% success rate in 10 minutes. I also want to emphasize that this includes training time. So this is going from has never heard of Helena ever before to has now done whatever tutorials or documentation reading they needed in order to actually complete the thing and completed the task. So that's the gap that we're seeing there. So that gets us through goal 1. What about goal 2? How do we make sure these programs are robust as web pages change? So for the case of the tables, we get to take advantage of this sort of similar structure. That gets us a lot of the way there. But what about for something like on that Craigslist page where it's just individual nodes? Quick background on web pages. Web pages are trees. Each node comes with a map from features to values. And the unfortunate thing about modern web pages is that they are always changing. And they change in a lot of different ways for a lot of different reasons. So the reasons could be just redesign, obfuscation, A/B testing. Maybe it's just fast changing content if it's Facebook and it's user generated, or it's the New York Times and it's breaking news. But the kind of changes that we see are just everything, right? So the content can change. The structure of the tree can change. The values associated with the attributes can change. The set of attributes that are even included can change. All of these are changing all the time. So how do we find the node that we want? And here I want to draw a quick distinction between deterministic replay and generalizable replay. So you see a record time web page, you see a replay time web page that has changed. Something about the structure or the attributes or whatever has changed. And with deterministic replay, basically what you want to do is throw out what you saw at replay time, this new web page, and fill it in with what you saw at record time, because you're trying to reproduce a bug trace, something like that. And you just want to get back that same old answer that you had before. In generalizable replay, that's not what we want. We want to be able to adapt to this new input, and we want to be able to get the new answer. So this is what makes it complicated. So how do we find the nodes that we need? You may look at the Google web page and say to yourself, there's only one text box. Finding the search box should be easy. But the web is wild, and there are, in fact, 7 text boxes on the Google homepage. So the traditional approach to finding, say, the Google search box is you're going to assume that a few key attributes are stable. And of course, the gotcha there is that they are not, in fact, stable. They're changing all the time. So the key insight here is that all of this stuff, the internals, this is just a teeny tiny slice of the Google page, the Google web page, the homepage. Users aren't seeing this, so this can change constantly. Nothing about this changing is going to confuse the user. On the other hand, the thing that the user sees, the sort of presentation of the page, can't change too drastically without confusing the user. And so many node attributes affect page appearance, and so that's what we're going to take advantage of. So the classical node selector synthesis problem said, let's take the record time web page, let's take the target node, and let's use that to figure out a robust node selector that's going to work on future variants of the page. And we pushed and pushed on the DSL and on the synthesis approach, and we just could not get there with this problem formulation. So we tossed that out and made the Helena deferred node selector synthesis problem, where instead we wait until replay time. We can take advantage of the fact that at this point in time, we know how the web page has actually changed. So let's take advantage of that information to actually produce the selector at replay time. And so basically what we do is at record time, we just grab all the attributes of the target node that we can. And so that's going to be all the attributes that are built in, a bunch more that we construct, hundreds and hundreds of attributes. And then once we get to replay time, now's the time to actually score all of the different nodes on this fresh web page and figure out which one is most similar based on shared attributes. And we'll just pick the one that scores highest. And so this ends up getting us to much more robust web automation programs than the prior established practices. And you can see this is over the course of a month. And so basically, synthesizing the robust selector recording time, that just was a non-starter. That was not going to get us there. And so it all became about how do we find a new version of this problem that can be solved and produce robust programs. So let's move on from that to how do we make programs both robust and human readable at the same time. So we've talked about usable drafting tools. Let's now move on to learnable languages. Why do we want them to be learnable languages? So one reason is we might be in a DORA workflow where we actually need it to be learnable so that the user can tweak it and reduce the ambiguity that we got from their earlier specification. But we also might just want that because the user wants to actually trust the output of their synthesizer. And of course, it also changes the class of programs that we can tackle. So before, if it was a small output, then we could inspect that and we could use that to figure out if our program was correct. But if we have a really large output, you know, we're scraping millions and millions of rows, maybe that's not going to be so comfortable. And so how do we do it then? Well, we want to actually be able to look at the program. So this is really important if we are doing long-running tasks, tasks with large outputs, or it's just high-stakes tasks, and you really want to trust the program. Okay, more web page background. When you do a click, what the web page actually sees is all of these gross low-level DOM events. Same deal when you're doing typing. And so when we are just doing something that we perceive to be click with mouse, what's actually happening is all these low-level DOM events are being raised at a lower layer, the browser internals layer. And unfortunately, we as the automator, the sort of bot that's controlling the web page, we don't have access to this sort of higher level API of click with mouse. What we have access to is the lower level. And so the standard approach here is you look at what the user actually did, all the low-level DOM events that were raised that we watched, and you say, oh, this slice looks like a click, and this slice looks like a type. And then you put that into your program, and then when the time comes to actually run the program, you basically map that click action to, here are a bunch of simulated events that we think will probably be like the click event. The problem is that this sequence of DOM events that is actually triggered changes. I'll give you some quick examples. So here we are on the right, we're seeing sort of the low-level DOM events that are being raised by clicks on different elements, and you can see that it is not the same, even though we're just doing clicks on different elements. And you don't even actually have to change the element that you're clicking on. So here we are just clicking on the same item on Google and getting a different set of low-level DOM events. And unfortunately, because web pages are just so interactive now, they can respond to any of these low-level JavaScript events, and some of them do. So we get into this conflict, right? Because what we actually want to show the user is this high-level, readable, manipulable version of the program. And then what we actually need to have in the program in order to make it robust for replay is this low-level, gross DOM event stuff that even programmers don't want to see. So what do we want to sacrifice? Who thinks that we should sacrifice robust replay? Raise your hand if that's what you want. All right, we've got one vote for that. Who thinks we should sacrifice readability? Yeah, no one seems to want to sacrifice that. Of course, you're right. We're not going to sacrifice either. But the way we're going to avoid sacrificing either is we're going to give up this idea that we're just going to have a single domain-specific language for this task. Instead, what we're going to do is a bi-level DSL. So underneath, we have this low-level language, which is what our synthesizer actually produces. We're then going to compile this in reverse to the high-level language that is going to be more comfortable for the user that they can look at and tweak. And then there are some edits that they can do that actually get mapped down to low-level language. And then, of course, there are some non-web statements that don't actually have to do any interaction with the web, and so those don't even need to be translated down. And so this lets us synthesize these really big, messy, complicated programs, but still make them readable and editable for people who aren't comfortable actually playing around with all those low-level DOM events. And the outcome, of course, is that Helena does handle modern interactive pages much better than tools that did not have this mapping to the low-level information that we actually need. I want to be clear that this prior state of the art, this was developed before the web got as interactive as it is now. So it's not really reasonable to expect, this was a tool called CoScriptor. It's not really reasonable to expect that CoScriptor would have solved this problem. This was basically an unsolved problem before. This just wasn't something that they needed at that point in time. Now we don't get all the way to 100%. You may be pleased to know that you cannot, in fact, transfer funds from your bank account if you are logged out. But obviously there was some stuff that was being left on the table by the prior state of the art. And so this was really all about going from unlearnable language to make it a learnable language so that the user can actually play around with it and tweak it. Okay, now that we've got that done, it turns out if you make a fun tool like this and you start giving it to real users, pretty soon they start wanting to tackle really large tasks, really long-running tasks, and still want it to be fast, and you start thinking about giving them parallelization. So raise your hand if you think this is going to be a CPU-bound kind of a process. Yeah, I agree, not really CPU-bound. What about if it's going to be about network latency? Yeah, I agree. And so that's really going to help us, right? Because that means that we can actually get really dramatic speed ups running this, you know, in parallel on our own home laptop. And so that's really helpful for us. The bad news for us is, who here thinks that if you grab the URL that you're looking at on the web page on your browser right now and paste it into another browser, that you're going to get back the same web page? Go ahead and raise your hand if you think that. Yeah, so not so much. And so that's the bad news, because in the past, what you would have done in order to sort of communicate tasks between multiple parallel workers is use the URL. But the modern web is interactive and stateful, and we really just can't do that anymore. And so this is this very strange transferless parallelism problem where, you know, you just can't transfer work between workers, because if you grab the URL from here and you pop it in over here, there's no guarantee you're getting back the same thing. But of course, you always can transfer work from the server to the individual parallel workers. You can always go to the web page and get something back. The problem is that the server is allowed to change all that data, and in fact, it does. So interestingly, if you scrape all the sort of the top 1,000 Yelp restaurants in your city, you will get back, even if you start these parallel workers at the exact same moment, you will get back 11% different restaurants. So unclear exactly what that top 1,000 is, but there's churn all the time. So this is a really weird parallelization problem. Even for a coder, it's a pretty weird one. So how do we ask these users who have really barely thought about parallelization before, have kind of a vague idea what it is, how do you ask them to parallelize? And so I pushed and pushed on sort of getting them to use any of the traditional approaches that we as programmers would use, and just couldn't get there. And then one day I had a side conversation about how would you deduplicate this data set? And it turns out that's a very familiar task for them. So I said, okay, let's steal the information that they would use to deduplicate the output data from these scraping scripts. Let's actually use that to transparently parallelize their scripts. This may seem weird. These seem like very different tasks, parallelization and deduplication. But really the key thing that unites them is that you just want to say, don't redo the same work that you've already done before. Now, defining the same work is hard, because like I was just saying, data is changing constantly. But the user can tell us what makes work the same, what makes an object in the web page the same, what code operates on each object. And so what we're going to do is just say, if we're encountering an object that has already been claimed, go ahead and skip it. Otherwise, you can actually do the thing that interacts with that object. So this is sort of the textified version of the same author's paper script that we've already been playing with. We're adding, sorry for the bad highlighting there. We're adding the skip block, which is the language construct that I introduced for this, the parallelization construct. And here we have these key attributes, the author name, the author institution, and it's just saying, if you see an author that has the same name and the same institution, assume it's the same author. And then here's the block of code that actually interacts with the author. And then when the program finds an entity, it decides whether to scrape based on whether anyone else has claimed it. So we keep our little claim log over on here on the right, and the worker 1 encounters UID 1. That hasn't been seen before, so they get to run it. Worker 2 can't get to run it because they've already, it's already been claimed. And this basically proceeds exactly how you want. And of course, you don't actually have to do it with a claim log. You can do this via hashing. It turns out, because data churn is so constant, this actually, whether you do it with a claim log or hashing, will actually change the output data you get. It's wacky on the web. So basically, what we did here was replace what people used in the past, which was this parallelization strategy, with a deduplication strategy, which is much more friendly for the user. So now that we can get big data sets, we can answer, when do CS researchers peak? At first, it doesn't look too promising. It looks like people are peaking pretty early, but it turns out that's just because people have different career lengths, and so it's going to vary based on career length. And so now if we break it out so that on the y-axis we have the year of the most cited paper, and on the x-axis we have the career length, then we start to see that impact, age, and experience just keep helping, which is encouraging, at least for me, as someone who wants to stick around a nice long time. But of course, that's not actually how we evaluate the parallelization. So here is what's happening. So we can look at, basically, as we scale the workers, are we getting good speed ups? And yes, except you can eventually reach the point where it's CPU bound. So this is a Twitter one where if you load 1,000 tweets into an individual Twitter page, it actually gets really big, not in terms of inches, but in terms of number of nodes. But if you distribute it across multiple machines, you get right back to the ideal. I've also started playing around with actually making it basically interactive time. So all of these orange bars you can see are actually under 1 minute. It's not really optimized for fast startup, but it looks like it's within range if we wanted to optimize it for that. You can also use the skip block, the same language construct, for a bunch of other uses. So it turns out failure recovery is really important for these users. You know, they're sending the undergrad home to run this program on their home laptop that's connected to their home Wi-Fi. It goes out in the middle of the night, you know, in the morning they have to restart and they don't want to go back and do it. So you can use the same mechanism to actually fast forward over the work that's already been done. Incrementalization, so I didn't show how we can say actually only scrape this if it hasn't been scraped in the last 3 weeks, or only scrape this if it hasn't been scraped in the last 3 runs, but we can set up a skip block to do exactly that, and that can get us really good speed ups. I also want to emphasize that adding skip blocks really is super easy. So if we actually, this is how it looks in the real tool, and the user is just saying, okay, based on the name and the institution, I think is what they're clicking on, then they can just press this add skip block button and it's in there. So that's really as simple as it is, and the user study results really bear this out. So you can see they're taking, you know, 8 minutes to learn it, but then after that, you know, they've practiced a few times, and by the end they're parallelizing a program in under a minute. So the gray dots are non-programmers and the orange dots are programmers, and even the non-programmers are parallelizing in under a minute, which is pretty impressive. So that gets us through goal 4. I'd be happy to keep talking about a variety of other things, including sort of where I see the future of PL plus HCI is going, but I see that we've sort of run up against time, and I'd love to do questions instead.
I have a question.
Yeah.
So you talk about the error rate, 85%. Is that, would we assume that 85% of the scraping tasks would fail, succeed, 15% would fail, or is it that you get a 15% error in your data? What does that look like?
Are you talking about the sort of the pie chart where I was talking about?
Yeah, you had like, I think the goal to.
Yeah, that's programs that would succeed. So if a program isn't going to succeed, you know, the first time you run it is when you figure out if the program is actually going to work, given the way okay, there's one exception to that. So the exception to that is that the web page can change over time. And so if you know, keep running a program every single day for months and months, and the web page gets redesigned, then all of a sudden you'll stop seeing data from that same program. And then you have to go back in and basically redemonstrate for the new version of the web page that has this new design. Obviously, like I talked about, there are ways that we can adapt it. So there is some amount of correcting for the way the web page changes. And that was sort of that similarity approach to node selector synthesis that I talked about. But once you cross the point where a human user would be confused about the redesign, you also cross the point where Helena would be confused about a redesign. And at that point, you do just want to make a new script. That's a really good question.
So the question I have is, you know, we see a lot of machine learning or AI work where you have 85% accuracies, and people are generally pretty happy with that. When it comes to users, tools in users' hands, that ends up being, I mean, I think even a 2% error rate could be a problem. So what, in the hands of your collaborators, what does that look like when they see programs failing, you know, for this or another reason? Does that encourage dropping to you know, the tool, or how do they deal with that?
Yeah, that's a great question. So for the case that I sort of just talked about, where it worked for the first X times that they ran it and then the web page changed, that's a straightforward fix, right? They just go back in and they make the new version that runs on the new web page. The much harder thing is if the web page is, so sometimes we'll encounter things like what I was talking about, where you know you suddenly gotten logged out of your bank account, and so you can't do the bank account transfer, or you're trying to bid on a closed auction, and so that just doesn't make any sense to do those replays. Usually people aren't picking tasks that would end up having those problems. The login problem is a real problem. So that's one where for users who are trying to collect data that is behind a login, we actually, you know, remind them to always log in before their data collection program runs. For something like bidding on a closed auction, you know, you're never going to get around that. That's just doesn't make any sense as a task. So it's sort of a case-by-case basis in terms of what is the kind of error that they're running into. Oh, I think you're muted.
Oh, I said thank you.
Oh.
So I wanted other people to ask questions.
Yeah. Sounds good. I think did Sam have a question?
Yeah. Hi. So one of the first examples in your talk was this thing, and maybe I didn't understand the example exactly, but there was a product on Amazon, and when you clicked to a different variance, there was kind of a race condition where you can't add to cart yet.
Yeah.
And I don't know if so I guess I have two parts to the question. The first one is that I don't know if I see what about Helena like addresses that specifically. So can you clarify that?
Yeah, great question. That's something we didn't even cover in this talk. Like I said, there are a lot of things that drove the development of this tool.
Yeah.
So basically for that, the best solution we found was to do a bunch of runs of sort of the straight line trace offline, where we are varying the timing of our individual actions relative to the AJAX requests that are going out. And so if you, every single time you run it with AJAX request A before event 1, and it fails unless you're waiting for the particular AJAX, then you can go ahead and say, okay, we can eliminate this dependence. And so basically you keep basically messing around with the timing until you figured out the patterns of this AJAX either always seems to appear before this event just because it's fast enough, and so we can go ahead and say it depends on that, or it seems to be required because if we put it before that, then it fails.
Okay, interesting.
Yeah, so it's offline testing.
Yeah. And then there was something kind of related to that was I can imagine maybe a slight variant of an error happening in that kind of use case where some kind of AJAX request successfully goes through, but it's for the wrong item. And then there's like this kind of subtle bug that would be happening where a cursory glance looks like it's getting the right information, but maybe it's not. And so later when you talked about how you wanted to build trust with the user by having this program that they could look at, I'm still kind of wondering questions about like, for I don't know, like if my mom were to use the tool or something, like what kind of trust would she be able to establish, or do you really still need some level of expertise? And then kind of also when you were doing the experiments, did you ask as part of the tests if the users felt like they believed in the data scraping?
Yeah, great question. So we did, and they did in part because they were actually running it to see if they got the data that they expected. So it seems like even though we expected that looking at the program was going to be enough, you know, these were programmers, and still they felt more confident in it because they were running it and seeing the end results. So it's interesting. This was particularly for the one where we were comparing sort of traditional programming versus Helena, and even there with experienced programmers, they were still more trusting based on seeing the results, which is very
cool. Yeah.
Can you remind me again of the first question there?
Well, so I guess it's kind of related to that part of the answer where I was, if the programmer expertise
is actually delivers the wrong data.
Yeah. I don't know if I actually asked a very focused question, but that was one part of it too.
No, that's a really good question. So it turns out that this is this weird collaborative program that is partially made up of the scraping program and partially made up of the server program that we just don't know. And so there's a certain extent to which we just have to trust the server, right? So at any point, it can start just giving us cat pictures for everything we ask. At the end of the day, we do need users to actually have some way of, and this is where the particular target audience really matters, and the fact that these users are really comfortable with and familiar with basically validating and doing quality assurance on the data sets that they get from, say, surveys and that kind of thing. So that's the sort of thing that they're actually really comfortable doing. Because basically all of them do end up doing post-processing to say, okay, you know, did we get the reasonable results that we expected?
Okay, cool, thanks.
It's the same you would need for any scraper, right? Whether you built it with this tool or you built it with traditional programming, you're always gonna be doing some amount of, you know, has the web page suddenly changed and do we still trust the data that we're getting? You have to have some sort of quality assurance.
Yeah, okay.
It's a great question. I think there was another question. Oh, I think you're on mute.
Not on mute.
Oh, now you're not on mute. Okay.
Okay, you can hear me?
I hear you.
All right. So one question I had was, it seemed like in goal 1, what you were really doing was your language was allowing you to select a portion of a hierarchy and then print it.
Yeah.
And so that's a very weak form of a tree transducer, say. Yeah. What about selecting a portion of a hierarchy and then transforming it?
Yeah.
It seems like you have an opportunity, but maybe you haven't taken advantage of.
Yeah. So there is a bunch of really cool work on that. A lot of this has been coming. Do you know Qianlong Wang?
No.
Yeah. So I would point you to his work. It is really, really cool. For whatever reason, a lot of the transformations seem to come out of the data visualization synthesis work. because that's sort of one of the cases where people are starting with nicely structured data, right? So they're not, you know, having to do this web page crawling process. They're starting with something that has some sort of structure, and they need it in some other structure in order to feed it into their visualization library of choice. So that's a great place to look for work like that.
But it seems like you are sort of almost set up to do the same thing.
Yeah, absolutely. Yeah, so we could absolutely have that as a post-processing step. And I think this is one of the things that I've been looking at a little more recently, is basically how can we apply this to get not just sort of these tabular data sets, but more graph structured data, especially because you'll run into pages like, you know, imagine an IMDb profile page where you want to go and you want to grab, you know, all of the directors associated with the movie, and then you want to grab all the actors associated with the movie, right? So you have all of this different sort of nicely graph structured data, and why shouldn't we be able to extract that too?
So I had a quick question about your deferred synthesis. I think I would have called that differential synthesis. You're taking the two trees and doing something.
Yeah.
But when you had this graph of success over a number of days, were you always doing it with respect to the day zero version? Or did you also try updating to the day K version and then doing day K plus 1 with respect to day K as opposed to day 0?
Yes, so this was running every single day. We were updating the synthesizer, updating the synthesized selector based on the web page that we were looking at that day. Yeah, that's really important.
No, but it has to do with day 0, day K, and day K plus 1. So is it day K plus 1 versus 0, or is it day K plus 1 versus day K?
So this matters for the other tools that we were comparing against. I'm trying to pull up the graph. Oh, where'd that go? So for the other tools, they're basically synthesizing a selector that we then run repeatedly over, here it is. So for these ones, they're synthesizing a selector on day 0. And then we keep using that selector over time, and it sort of becomes less and less effective over time as the web page changes more and more.
Right.
The point of our sort of deferred synthesis or differential synthesis approach is that every single day we are making a fresh version based on the individual web page that we are looking at that day.
But so since there was a degradation of 80%, you know, on day 1,
yeah,
I would have thought that there would have been continual degradation if you do it that way, as opposed to like a constant 80% if you did it with respect to day 0.
Yeah, so what happens here, so we don't show sort of what happens if we run the Helena approach actually doesn't synthesize a selector at the time that we're viewing the record time web page, right? It only starts synthesizing selectors once we say a replay time web page. And so this is this number, right? The very first time we run it, which is actually the same day, we load a fresh web page, and then we try, in our case, synthesizing a new selector, or in the case of the other ones, applying a selector that they have synthesized already based on sort of their training time web page. The reason we
why wasn't there also an 80% degradation from day 11 to day 10?
That immediate drop is that some of the nodes just don't appear when you reload. So this was basically every single node on it. This wasn't sort of the normal nodes that you would be clicking on in actual script. This was every single node in a web page that you can click. This was thousands and thousands of nodes. And it turns out that a lot of those nodes just never reappear on first reload. And so that's why you see that immediate drop.
And is that because of caching or some other effect, or?
No, it's just these are the nodes that, you know, they appear because of this, you know, time sensitive, right? We went on Facebook at this time and it had these posts, and then we came back at this other time and it no longer had these posts that were at the tail, and it had new posts. It's just that kind of thing. It's incredible how quickly web data changes. Just the amount of churn is wild.
Interesting.
That's a great question, though. No one ever asks me that, and I always wish people would, because I think it's really interesting just how quickly the web is changing.
All right, we're kind of out of time, but Justin, do you want to shoot the last one?
Yes, I'll ask a very quick question. Thanks a lot for the talk. I thought it was very interesting. I wanted to ask a more specific question about your third goal, where you have these two DSLs, one for the higher level and one for the lower level interaction. So I guess you were pointing out that they look very different because they're trying to capture, you know, very different modes of interaction. And I was wondering how you managed to do this kind of synchronization between the two. So looking at it at a very high level, looks like maybe some kind of lens work could be used when you're updating one program. You would like to propagate that to the lower level program, or maybe something like this. I'm just wondering if you think that might be useful here, or whether you looked at these kind of things before.
Yeah, I think absolutely. So basically what ends up happening, I'm going to show you on the illustration. What ends up happening is we have to maintain that slice of the low level program. So each of these high level statements actually has an associated slice of the low level program. And we maintain that mapping throughout. You know, we never throw that away, because if we threw that away, we would never be able to do standard compilation to go from the high level to the low level. But then, yeah, so when the user, you know, changes from typing this string to some other string, that gets propagated back down to the low level, and we replace it with all the keyboard events we would need for the new string, right? And so, yeah, absolutely, lens stuff makes a ton of sense for this.
Cool. Thanks a lot.
Great question.
Cool. Thank you so much, Sarah, for joining us today. Very nice talk.
Thanks for having me. It was great chatting with you all.
Thank you.
Yeah, thanks.
Thanks a lot.
I'll also give you a virtual clap.
Yeah, we should do that. A virtual clap. Yeah. And I guess I'll stop the recording now.